oh, can you give me a mic from over there? And go to presentation. Good morning, students. Sorry, starting a little late. I have some stuff to talk to you about concerning exam 2 that we took last week in emergency status. And we're going to talk about thermal equilibrium and stuff today. But before we do that, I want to do the angular momentum demonstration. Go ahead and turn all on, please. Okay, and I'm going to pause the podcast. Okay, so that was the angular momentum demonstration. And now you've seen it for yourself. And it's very similar to the ones that are in YouTube. So I highly recommend you look at that. Okay, about exam 2. And I have to apologize that we had a fiasco day on Thursday last week, but it took me a couple hours to get this ported over to web courses. 526 of you took it out of 542 that were supposed to take it. And so that's pretty good. 16 people absent, 3% absentee rate. That's pretty good. So I'm happy about it. The average was about where I figured, 70-something. And I graded it. And also, there's a discussion post about the brain burner, and that was bonus point activity. So even if we drop your exam 2, you're going to keep those bonus points, 5. Some of you got partial credit. I actually went through a big spreadsheet of all your answers for every single person that did it, which was 400 and something people. And I looked at every single one of them. And for about 24 students, I gave partial credit. There were a lot of you guys that got it right. That was good. I was hoping to burn a few more brains, but I guess you guys are getting smart, so that's good. So if you got that 5 out of 5, that's all slapped together into your exam 2 total in the grades page. Now, exam 3 on November 10th, that's our third and final midterm. We're going to have special study groups going for that, and it is going to be a regular pencil and paper exam. And hopefully we won't have any more fiascos like the triple whammy that happened to me on Thursday last week. All right, so we're back on schedule. And speaking of schedule, we now know the location for the final exam. And the final exam is going to be in this room for section 1. That's you guys, the morning section. So make a note of it. You'll just come here, okay? You'll be taking, just like a midterm, except it's a 3-hour test. 100 points, 3 hours to take it, so a little bit more time than usual. Anyways, you'll just come right here. But it's on Saturday, December 10th, at 1 o'clock, so not our regular 10:30 or even 10 o'clock start time for the final. All right, so I'm going to try to remind you of this every day. Now, the noon section, they're going to be down the hall in classroom building 2, room 201, so that'll be good. All right, any questions about the final? Okay, let's keep going. I want to talk some more about thermal properties of matter, heating and cooling and stuff like that. We didn't get to do as much last week as we wanted to because of the hurricane. Canceled lecture 2 Thursdays ago, so we're still ahead of schedule. We're doing good, and we're just a little bit. We just have a little bit of chapter 6 to wrap up today. So last Tuesday we talked about phase transitions and stuff, melting point, boiling point. We talked about latent heat of fusion. And we began to talk about this idea of heating up substances. Now, the only substances that we really talked about were H2O, water. And we talked about water ice and water liquid. And you had a couple cinchy questions about that on the test. I didn't put any really tough questions on the mostly concepts, except for that one brain burner. That one was a toughie for some of you anyways. So I talked about the e pluribus unum concept. Go ahead and write this down in a little table. And I said that the view is that, we can't really see molecules. They're so tiny, they're submicroscopic. But we assume that they have kinetic energies, that they obey Newton's 3 laws of motion, F equals ma, and so forth. And then we apply statistical methods. Raise your hand if you've had a stats class here at UCF. Okay, that's a bunch of yous. Good. And, in stats, you use all kinds of different tricks and stuff. And here's the formula that actually expresses the connection between a zillion tiny kinetic energies. So this is the pluribus column. Pluribus meaning many. From many kinetic energies, we extract a temperature. And it's actually the average kinetic energy. And the formula is, after a bunch of trig, and after a bunch of calculus, and after a bunch of stats, that the average kinetic energy is 3/2 times a constant K, which I'll talk to you, it's called Boltzmann's constant. I'll show you what it means in a minute. And then times the temperature of the gas. And that is the temperature in the Kelvin scale. Okay, so 3/2 kT. The other thing that we talked about was the exchange of momentum and pressure. We talked about that first, actually, Tuesday before the hurricane. The law that expresses that pressure doesn't have any explicit momentum states in there, but it does have a temperature state in it. It's called the ideal gas law. Pressure P, little p, times volume V, capital V, equals capital N times kT. And here's just a little blurb about what K is. It's called Boltzmann's constant. And we're not going to do a huge amount of calculations with it, but you can jot it down. 1.38066 times 10 to the minus 23 joules per Kelvin. So it's energy per Kelvin scale temperature unit. Capital N in the ideal gas law is just the number of molecules in your container. So if you think about it, that ideal gas law, the pressure depends on how many molecules you've got, capital N, how much volume you've got, okay? And if you compress down the volume, you're going to change the pressure, okay? And then it also depends on the temperature, and in other words, the average kinetic energy. So this is known as the ideal gas law, and we will not be making a huge number of calculations with it, but there is a formula, and it's important for us to remember that these two formulas and many others that we could write down are part of the result of applying this e pluribus unum principle. Now, the guy that figured out the e pluribus unum principle is named Ludwig Boltzmann. I know, 150 years ago. And you can see he was a pretty stern-looking guy. But he's the one that came up with the idea, yeah, let's treat these molecules that we cannot see as if they're little billiard balls that obey F equals ma and everything else. Let's study their kinetic energy. Let's study their momentum interactions. And let's try to sum up and get one macroscopic measurement from them. And the ones that we've talked about are temperature and pressure. And there are other ones. Here's a picture of this is his grave, and I guess it's in Vienna. And that's his famous equation, S equals K times the log of W. Now log, that means logarithms. We're we're not supposed to talk about logarithms or calculus or trig in this class. But this is, and capital S stands for entropy. If you've ever heard of the word entropy, E-N-T-R-O-P-Y, this is the guy that came up with the idea. And capital S is the symbol that we frequently use for entropy. And then capital W is the number of dynamical states in a given sample of gas or whatever it is you're studying. So now we don't have to worry about that equation, but this is just a little background on Professor von Boltzmann from Austria. Very interesting guy. And it's kind of a sad guy too, kind of a tragic figure. But he looks pretty ferocious in this picture though, right? His gravestone. Many scientists go there, they get their pictures taken there in honor of Boltzmann. Okay, now I want to talk about the flow of energy or heat transport for just a little bit, thermal equilibrium. And we remember from last Tuesday, a week ago, that Joule was able to calculate the thermal equivalent of work by stirring up water with a pulley device and a weight that fell to the ground and deposited a certain amount of kinetic energy into the water, and then he measured the temperature. And so stirring up the fluid leads to an increase in temperature because the kinetic energy is changed. Another basic concept is that we need for figuring out energy that's changed or energy states, heat that flows, is the idea of thermal equilibrium. So that's number 2 here. And basically, two objects at different temperatures are not at thermal equilibrium. And what does that mean? Well, if the temperature of substance X, and by the way, this is in chapter 6, part 10, if the temperature of substance X in this little diagram here to the lower right is less than the temperature of substance Y, then thermal energy flows out into X because it's cooler, and it flows out of Y because it's hotter. All right, and so if you think about it, if you think about it like Boltzmann might have thought about it, you would say, all right, those molecules that I cannot see, whether it's a gas, liquid, or solid, they have kinetic energy. And the faster ones, if for instance in a gas, the faster molecules are going to tend to migrate over to X more rapidly than the other ones to Y. So there's a lot of fast molecules from the high temperature gas, Y, and relatively small amounts. So make this little arrow, the lower arrow here, a little bit more feeble to indicate that those molecules in low temperature gas X, they're a little bit pokier on average because it's a lower temperature. Okay, so lower kinetic energy, and that means that on average, and that means that on average they are not getting from point A to point B very quickly. All right. Now, more kinetic energy is going to tend to go over towards the cooler gas X, and not as much is going to get transferred over to Y from X. So eventually, their temperatures, the average kinetic energies, are going to be the same. And that's when we say that the temperature of X and the temperature of Y are equal. And that means that they're still, those molecules are still buzzing around in there, okay? But now they're so thoroughly mixed that the averages are the same for the two substances, and the kinetic energy swapping is equal from one to the other, right? And when that happens, you're at thermal equilibrium. And just a side note, you can see down here at the bottom of the page, I put a little blip down there so you know the section of the textbook, the e-text that we're talking about. Now we're going to do some more work with calculating thermal equilibrium. Probably on Thursday we'll do a little bit of this. And you've got some big homework assignments coming up. You've got a fair-sized one ready for after class today. It'll be ready at 11:50, homework 11. And you're going to have homework 11.1, which I'll disperse on Thursday, and you'll have a couple weeks for that, kind of like the last time we had an extra assignment. But what I want you to do is, on the topic of equilibrium, study example 2 at the end of chapter 6. And hopefully that'll make sense to you. And we'll kind of review a little bit of this example 2 at the beginning of Thursday lecture. And then over the weekend for homework 12, you'll have some thermal equilibrium temperature calculations. And by the way, the processes that we're going to work out today are, because I was hoping to have today's calculations on exam 2, but we missed a lecture, strategic lecture, right before, or the Thursday before, due to the hurricane. So it's going to be on exam 3, and it's the question of heat melt heat, which is traditionally one of the 3 or 4 real brain burners that students in this class encounter. So we're going to work on that now. So let's get back to this idea of specific heat. And we talked about this kind of in a stealth mode on Tuesday last week, because we talked about, the fact that water takes 1 calorie, liquid water, to raise its temperature gram for gram by 1 Kelvin. All right, that's how we define the calorie. And that's heating up from any source that you can name. And it's the same, Katerina, you could also say that it is the amount of energy that you have to extract by refrigeration to cool water from 15.5 Celsius down to 14.5 Celsius on a gram for gram basis. So that's the calorie. We talked about that last time. The number that, or the physical property of matter that encodes that, how easy is it, how much energy do you need to raise 1 gram by a certain, amount of temperature? That's called the specific heat. The symbol is the letter C, and the specific heat of water is 1.00 calories per gram Kelvin. By the same token, if you measure the same property in water, solid water, otherwise known as ice, it comes out to 0.50 calories per gram Kelvin. And there are scientists that make make ultra accurate measurements of specific heats because it's actually a good investigative tool to know the thermal properties of certain things. Now, as I mentioned last time, the difference between liquid and solid is the arrangement of the molecules. And in the case of water, it's crystalline bonds that form at a certain temperature, or can form only at a certain temperature, 273. And they can only be busted up at a certain temperature, 273 Kelvin. Okay? So below that or above that, you're talking about solid crystalline bonds, and above that, you're talking about liquid with cohesive bonds, very weak intermolecular bonds, intermolecular forces. And I made the comment last time that this is all the interplay of electrons and protons in different water molecules. So H2O to H2O It's electrons talking to protons, and it leads to these intermolecular forces and electrical potential energy. And this is my final comments about this, is that these intermolecular bonds, you can think of them as storing a lot of energy because, you know, if you think about a crystal has a certain geometric proportion, and if you looked at the idealized view of a crystal, a cell of a crystal, it has a specific set of dimensions. In other words, the H2O molecules get a certain distance and no closer. You know, plus or minus, you know, they may jiggle a little bit, but they get to a certain distance and no closer. And that is like in gravitational potential energy. You know, you have the energy of position. You know, a certain height, you're at a certain gravitational potential energy above sea level or above the floor here in the lecture hall or above any surface that you care to define. And it's the same thing with crystals. And so thinking about them as stored energy or electrical potential energy is a good way to do it. And you can see that, as I mentioned last time, in terms of latent heat. And I told you that the latent heat is the work necessary to force a reorganization of the water molecules or whatever substance you're talking about. In fact, if you're talking about gold, then you're talking about atoms, because gold is an element, it's not a compound. Now, there's a problem with this table, and I want you to make a note. This is the table from page 93. I just noticed it this morning that the textbook publishers messed up my table. And there's a whole bunch of typos here for ethanol, copper, gold, and lead. And so make a note that those, I think everything else is kosher, but that particular part of the table, they must have used somebody else's data, because it's not correct. And I have an accurate table for you in a few slides. But to reinforce, the latent heat expresses the fact that every gram of substance needs some energy to either melt it or vaporize it. So every gram of water has a certain number of water molecules. And if they're frozen together and bonded, you could actually count up the number of molecules. I mean, theoretically you could. It's a huge number. You could count up the number of molecules and the amount of work to separate them. Okay, so it's like, you know, like making a peanut butter sandwich. You know, you need two pieces of bread and some peanut butter, and you can measure the amount of peanut butter you need by, you know, how thick you put it on and stuff like that, and multiply that by the number of sandwiches you got to make. You can tell I'm talking about food because I haven't had my lunch yet. I'm kind of hungry. I ate real early this morning. But it's the same kind of principle. Every gram is a certain number of molecules bound together, and every pair of molecules bound require a little bit of work to break apart. Right? The sum of all that is the latent heat. So a certain number of calories per gram is appropriate for latent heat. Similarly, in terms of heating, the same thing is expressible for different substances. Every gram of a substance needs some energy, Q, to raise the temperature by 1 Kelvin. And so that amount of energy is expressed in the specific heat. All right? Now, let's go through the general heating up procedure. Here's the heating up equation. The heat energy equals mc delta T. Okay, mass is m. How much do you have? Okay, so if you have a big sample to heat up, you need a lot of energy. If you have a smaller sample, you know, you don't need as much. This is measured in grams usually. In this class, but you know, an engineer that's building a bridge might think in terms of kilograms or even metric tons. For instance, I was reading about the Hoover Dam out in Nevada on the Colorado River. The Hoover Dam, apparently it was made like 80 years ago or built 80 years ago or something like that. And apparently the concrete that they poured for that, huge amount of concrete, it's still solidifying. It's not completely solid yet. It's still in the process of transforming. It's a chemical reaction of making that concrete really hard. And those guys have to take into account the temperature of the concrete and stuff. And they have to know, is it going to be, when will it be strong enough to hold back that entire lake of water, that huge reservoir of water that they have up there. Okay, so those guys might be working in terms of metric tons of concrete, but for us guys here, it's going to be grams. Now the other thing is, you've got to know what kind of substance you've got. Some are easy to heat up, like gold. Some are tough to heat up, like water. And that's encoded in the specific heat, C. Right? So for instance, metallic copper, the specific heat is 0.093 calories per gram Kelvin. Right? And I believe that was typoed in the table of the textbook. So make a note. And make sure you don't get deceived by the typo in the textbook. And then the other thing, if you want to figure out how much heat energy you need to heat something up, or how much you have to refrigerate away to cool something down, so that would be a negative Q. You have to know how big is your heat up, or how big is your cool down. All right, that's delta T. And this has to be in the Kelvin scale. And when you're looking at your homework tonight, homework 11, you'll have grams of ice to convert into grams of water at a certain temperature, starting at a certain temperature, finishing at a certain temperature. And we'll be doing some practice in just a few minutes with that. Brandon. Right. Do we do the same thing with temperature depending on? That's correct. If you're cooling down, temperature final, TF, is less than initial temperature, T subscript I. So T subscript F minus T subscript I, in that case, would be a negative number. And that means that Q is negative. And so when something's cooling down, you're going to have a negative Q. And that simply means that you have to extract that. Okay? A positive Q means you have to burn it in there with a flame or electric heating, equipment, stuff like, or sunlight. So sunlight is a positive Q. And you know what's a negative Q? Midnight. Extracts heat. If it gets cool enough, it'll extract heat. Or water, the ocean water. You can get hypothermia because the ocean, the ocean is cooling you off, and if it cools you off enough, it can kill you. Anyway, so those delta T's, cool down or heat up, are in kelvins. Now we're going to work out an example here, and I want you to take very careful notes. This is the heat up equation, Q equals mc delta T, and we're going to use that for whenever we have something that we have to heat up. We have to know how much we have. We have to know what we have, what the substance is. And we have to know how much we're going to heat it up. All right, so let's try an example. We're going to heat a small piece of ice, 10 grams, 0.010 kilograms. And go ahead and sketch this diagram. We're going to start, Brandon, down here at temperature T subscript I. So that's down low. This is a heating process. All right, we're going to heat up the ice, and then we're going to melt it all at 273 Kelvin. So when we're melting, the temperature does not change. All right, so I made that flat. The final temperature is up here. So we want to take a little sample of water and 10 grams of it at a temperature below freezing. We want to heat it up to 273. Excuse me. We want to melt it at 273, by, laser beams or sunlight or, propane flame or something like that. And then we want to keep heating it after it's melted as a liquid, and that's this phase over here. So the first slanted line segment, go ahead and make a note, this corresponds to heating up ice. All right? The second slanted segment over here on the right corresponds to heating up liquid water. All right? And you're starting at 273, and we're just going to go up a few kelvins. Okay? And in our example, we're going to start a few kelvins below 273. I can't remember what we actually have. Now, there's 3 chunks of energy required here. The first chunk is Q1 that you need to heat up the ice. Okay, so Q1 is heating ice. And that's going to be MC delta T. And we'll do that in a second together. All right? And then you're going to need a big chunk of energy here, Q2, for melting the ice. All right? Unless you have a big delta T, you don't have a lot, and you're working with ice, you don't have a lot of energy for heating as much as you have for melting. Melting is a big task for ice. And then the final chunk of energy is down here, Q3. That's for heating up the liquid water from 273 to whatever I say is the final temperature. All right? So this is kind of a strategy diagram of the calculation that we're going to work on. All right? Now let me pause for questions. Yes, Brandon.
Okay. So, let's recap. What's Q between MC and C?
The first Q is MC delta T. The third Q is going to be a different MC delta T. And I've got them outlined in the next page, so don't worry about that. But yeah, those are going to be MC delta T's. And then this middle Q is just the latent heat times how many grams you've got. All right? Question over here.
So if you were going the other way, like you were freezing ice, your Q would be negative, right?
The question was, if you were going the other way and freezing liquid water, making ice cubes, your Q would be negative. And the answer to that is yes, because then this would be Ti up here, and Tf would be down here. And so you've got negative delta T's, and so your Qs are going to be negative. And to freeze, you have to extract heat from the liquid water to turn it into, because when it's liquid, those things are still bashing around too fast on average to form a nice hexagonal crystal. Okay, so you got to extract a little bit of energy. And that's this middle Q here, right? And it would be negative if you're freezing stuff. So this is actually a reversible diagram. This is a heating diagram, and the reverse of it, just different direction, would be a cooling diagram. All right. No more questions? Okay. Let's look at this. All right, so here's our example. Here's my, let's use this nice, easy initial temperature, 266. All right, and let's make the final temperature 275. Now, in between those two is 273. All right, so we've got some heating, we've got some melting, and we've got some heating again as a liquid. All right. Now let's go through the process here. The first heating, Q1. All right, Brandon, MC delta T, here it is. Okay, and this is heating the ice. It's 10 grams of ice. It starts at 266, and it goes up to 273, so the delta T is positive 7. Here's the formula that you use. Now, this is I made this to be a fairly cinchy calculation to make. Okay, 10 times 0.5 is 5. 5 times 7 is 35. So, but whatever the numbers are, that's what you use, and you just, kind of crank them through. Question? How'd I get 70? Because my initial temperature is 266, and so I raise it from 266 initial temperature, I raise it 7 Kelvin to get to the freezing melting point. Okay? That melting point, if your initial temperature is below and your final temperature is above the melting point, you got to deal with the melting point. All right? So that means you've got a 3-part process. And this is the first part. We've heated up the ice. Now the ice is at 273. But it's not a liquid yet until we pour in some more energy. Right? Now we're going to save that calculation for last. Let's do Q3. This is heating the liquid water. And now we're going what's your name over here again? Yeah. Evangeline. Okay. Evangeline. This one is going to go from 273 up to my final, which is 275. So this one's going to be plus 2K. All right. And I just made it fairly simple so it's not too bodacious. Here it is, 10 grams. And we're assuming that we haven't lost, nobody snuck in and put a straw in and hydrated it up with any of our grams of water. So you still have 10 grams. And the specific heat here now look at here. Okay, C is different. This is liquid water now. All right, for Q3. And C is different up here in the Q1 calculation because that's solid water, otherwise known as ice. All right, 0.50 calories per gram Kelvin. So the only thing that's not changing in this is the mass. But you can have different delta T's, you just got to determine what your 2 delta T's are. This one is 5 and, no, it's 7 and 2. It could be 50 and 11, or 30 and 75, or 30 and 100, going all the way up from 273 to 373, at which point you start melting and boiling. You start boiling. All right? Question?
Wait a minute, where did 2K come from? Didn't we use 17 in the last problem?
Yeah, it's 2 different. Let's go back over here. We have 2 different delta. These don't look, these are different. It's kind of hard to see. I tried to make this a different size between this line here and this line here is a little bit more distance than the middle line up to the top line. But Brandon, your delta T's can be different. There's no, it just depends on,
Never mind, I just realized we went from 273K to 275.
That's exactly right. So you just got to look at the data, at what you got, and we got 275. So that means over here I've got 2K. All right? Now, we have to work out the change of phase. So this is going to be Q2. And I think, yeah, so 80 calories for every gram of H2O ice. Okay, we've got to add 80 calories of heat for every gram of H2O ice. Uh-oh, my notation is incorrect here. Let me see if I can change that quickly. Hold on a second. Q3, it should be Q2. Q2 is 80 times how many grams I've got? 10 grams. So 80 times 10 is 800. So that should be Q2, not Q3. I'll change that for the next lecture. Okay, so let's work out the total energy budget. Let's put them all together. Okay, we've done the two slanted lines, Q1 and Q3, and then we did the horizontal line for melting. That's 800 calories. So 35 plus 800 plus 20. And that works out to 855. So that's the total Q for this particular process. Now, if you want to make some tea and boil water and then put in your tea bag, well, then you've got a different delta T. Okay, so you can boil all the water. That's great. But your second delta T in that case would be 100 Kelvin because you're going from 273 up to the boiling point, 373. But in this one, it's 2 and 7 for the delta T's. So you got to just read carefully, and you're going to have a chance to do that in a second. Question over here. Yeah.
Can you explain how you got delta T one more time?
Yeah, delta T is the difference in temperature for each heating phase. Your first heating phase goes from the initial to the melting point. Okay, so 266 up to 273, that's plus 7. And then the second heating phase is after everything's melted as a liquid from 273 up to the final, which is 275, so that's plus 2. Okay, you're welcome. Question? Alexis.
For the 80 calories, how did you get 80 calories? Is that just something that you know for?
The question was, how did you get 80 calories for the, that's the latent heat of fusion for water, you know, so for the liquid ice transition. And it is different. You just got to look it up on a table. Okay, or you got to measure it in the lab or something like that. So that's one where I don't expect you guys to memorize that. I mean, you're probably going to remember for water, but like looking it up for copper or tungsten or something like that, no, you'd look it up in a table because that's what I would do.
For water, it's 80.
Yeah, for water it's 80. And for tungsten, it's going to be different one. And we had a table of this, the latent heats, you know, that we were just looking at. Question?
Yeah, so then how did you get the 800?
10 times 80. Because the latent heat of fusion is the amount of energy to, excuse me, let me repeat it for the podcast. The question was, how did you get the 800? And the way that you get the 800 is you use the latent heat of fusion. That goes on a gram by gram basis. It's 80 calories per gram. So every gram of ice, you got to bust it up with 80 calories of oomph, 80 calories of energy. And so if you got 2 grams, then you need 160. 3 grams, 240. 5 grams, you know, so however many grams times 80. All right? Question back here.
If there's no change in Kelvin, how did you cancel that in?
There's no change in Kelvin?
Yeah.
Where?
For your delta T. Why did you make common building?
Here?
For the 80.
Over here? You're not the question was, how did you get rid of kelvins there? The kelvins are not in that equation. Okay? The latent heat, everything is unchanging at 273. Nothing changes temperature until it's all melted. Okay? Nothing cools down until it's all frozen if you're going the other direction. All right? So the Q2 calculation, the latent heat of fusion, you just got to make sure that you're at the melting point. And then you just multiply by the number of grams you got. Okay? Another question. You know, I have a feeling that you guys are going to crush this stuff. I just heard somebody over here say, yeah, sure, Dr. B. All right. Let's try it. Turn your clickers on. And we're on frequency AA. And Turner, you come up here. You stand over here next to your boss, Miss Darian. Okay, Darian, I want you to make sure he doesn't screw up. Okay. All right. Actually,
Yeah, you can let him figure it
yeah,
out.
he's going to have to
first.
count. Yeah, go ahead and sit back down. It's not a multiple choice. Okay, you're going to try one of these calculations now, except you've got a different set of, a little bit bigger sample of ice. Here's your spec. Go ahead and. Okay, instead of 10 grams, you got 120. Evangeline, you've got a starting temperature of 260. All right, so your first delta T is 13 Kelvin. Your final temperature is 300. So Brandon, your second delta T is going to be different again. You got two different delta T's. One delta T up to 273, and one delta T from 273 up to the final. And then, of course, you've got latent heat of fusion. You better break out your calculators. Can you turn it all on, please? Could you give me my T? Thank you. I've been blabbing my big mouth for almost an hour now. And remember, when you're doing this, you're going to get a big number. It's going to be, because you got a big sample, 120 grams of ice. But just work it out the same way. Easy does it. And let's see if you guys can get it. Can you click the bar chart?
Press refresh.
Oh, wait a minute. Okay, sorry. Hold on a second, you guys. It's not multiple choice, it's numeric.
Oh,
Okay, so close the question. There you go. Okay, try it again, everybody. You should be able to enter a number now.
who were the 18 people who did it?
You just typed in a letter. Yeah. That means 18 people. I don't want to tell you what it means. Look at Alexis. Very nice. Evangeline Rockburn. Good. Good. I wish I knew more names. What?
You could just print out all their names and just read them off while they're doing this.
I've done that before. I've done it for attendance. Down in the big lecture, the big subterranean lecture hall. I've done that before. I used to do that, but
I haven't had a class in there in forever.
yeah.
Like, I haven't had a class in there since I took your class.
Yeah, I've been in there a few times since that. The famous semester with Shy in the front row with the Cheetos and everything.
That was my semester.
Yeah, it was.
I have no idea. I don't like talk to her very often. And I haven't seen her since she stopped doing SI. She might have just had too much on her plate. Or she might have graduated.
No, I don't think she was graduating. I just hope I didn't tick her off or something like that.
I don't think so.
Well, I do have a pretty bad reputation as a mean. Well, at least I try to. It doesn't really work all the time.
No, not too
Okay. This is good. Everybody's working.
Oh, so do you ever do physics 1 and 2 classes?
Yeah. Sometimes. Yeah, like I had physics. They wanted me to take physics.
You are on the thing.
They wanted me to take physics semester in one section of this and one section of physics 1. I persuaded him to let me do all physical science this year. But it just depends.
Let me know if
Are
you
you
do.
gonna take it?
I'm gonna have to
Which
take 1
one?
and 2.
2053 and 2054
I think so. That's just the standard college physics, right? Yeah.
with trig, no calculus.
Yep.
Yeah, I taught that 2 summers ago. In 6 weeks. Turner von Berwick, get your group up here now. Did you get your number in?
The 800 comes from the latent heat diffusion, which is 80, and then it was multiplied by the grade. It's always going to be 80, but it's not always going to be 80.
Press send.
Yeah, you press send.
Yes.
It showed me the check mark last time.
Okay.
That's it.
Okay.
What you could do is after class, you can check and see if it went through.
Yeah,
Don't
and
have a question, just have him do
I
it.
think we're Turner. I want you to stay. I think we're going to dismiss a little early today, so make sure you stay, and we'll be able to check your vote. Okay, 1 minute to go. See, this is interesting. You know, why are these answers coming up?
Well, what's 120 times 260? Those are probably people who just multiply stuff together. That's when I do when I don't know what I'm doing.
Just multiply random numbers. Nice.
Whatever sounds right. Well, that one, those 5 people just multiplied the 40 times 120. That's
Yeah, but
what I
where's
did.
40?
Between 260 and 300. They didn't split it up into 2.
Oh, okay. Yeah, you're right.
Yeah.
This must be a version of that as well.
Yeah, I don't
Ooh, look at that. Ding.
Did you just
So
change
this
what
is-
the right answer was?
No. Oh,
You did.
gosh.
There you go.
You don't want that.
Yeah, there you go.
I
Okay.
didn't know you could do that with this screen. So this is like a
Touch screen. Yeah, that's
touch
weird.
screen. That's a big
I
touch
did
screen.
not know that.
10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Well, it appears that 62% of you got it right. Very good. Raise your hand if you got it right. Very good. Very good. All right, a couple more concepts. Here's a good table of specific heats. Go ahead and write this one down. Take a minute. Solid and liquid H2O, we know. Glass. There's a zillion different kinds of glass. So, but this is an average value. Ethanol, we've talked about 0.58. Aluminum, 0.215. Gold, 0.0301 calories per gram Kelvin. Copper, 0.0923. Silver, 0.0558. And I have another clicker question, multiple choice. It's all right, we can still use this image. Not yet. Okay, and actually, I will start the question. Which is harder to heat up? Oh gosh, they don't see this. Oh yeah, they see this. Okay, okay, here it is. Which is harder to heat up? Of these 4, on a gram for gram, Kelvin for Kelvin basis. 30 seconds. Now this is analyzing a table. So on an exam, I would give you a table like this, like on the cover page, and then you'd have to turn back to the cover page to answer this question, kind of think it over, like you're doing now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, go ahead and stop. And nobody voted for A. Who voted for A? Yeah, okay, good. My software here looks a little bit shaky.
Yeah.
Yeah, aluminum, just look at these numbers down here. All right. 0.215 calories for every gram for every Kelvin if it's aluminum. But now down here for gold, gold is the easiest one because it only takes 0.0301 calories to take a gram of gold up by 1 Kelvin. All right? Next question. You have some ice at 250 Kelvin, really cold. How many phase transitions? Excuse me, phase transitions. 1, 2, 3, or 0? Wait a minute, 0. 0 phase transitions. Twenty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Whoa. You know what? This is the answer. But 44% of you selected C. There's only two fate. There's 3 states for here on planet Earth. So only 2 phase transitions if you're going from one to the other. Next question. You have some ice. And you want to heat it up to steam. So this time you got 3 delta T's. Because you got to go from liquid water to boiling water, and then from boiling water, from steam, you got to heat up the steam another so many degrees above 373. Twenty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. You know, you guys that voted late, most of you at the last minute, you voted wrong. This is the right answer, D. I was able to look at the bar chart. 53% of class voted correctly, but all of a sudden in the last seconds there, when I counted 10, the number of people voting for A went whoop, way up to 38%. I've got some good news and some bad news for you. The good news, the bad news is we're going to dismiss early. I know you don't like that, but the good news is we got homework. It's ready to go at 11:50. You're dismissed 6 minutes early today. See you on Thursday. Good job. Come on down to the front if you want to try out the angular momentum stuff. Can you do that?
I got to skedaddle.
Oh, okay. I'll try to supervise both.